Hello and thank you for watching. This is Mr. Hill dealing with ionic bonds today as our lesson. Let's get started. Well, what are ions? Ions are formed when electrons are lost and gained of an atom, or atoms lose or gain electrons, if you will. And the cations, of course, are positive, and the anions are negative. And typically, the cations are formed on elements that's on the left side of the periodic table. So you can see right there in 1A and 2A. And then on the right side of the table, we see groups starting at 3A going all the way over to 7A. And they form the negative charges. So what makes a bond ionic? Well, electrons are transferred. So like salt, for example, it actually can transfer one electron to another between the two of them. They usually involve a metal and a non-metal. Sodium is a metal and chlorine is a non-metal. Products are called salts. Anything that forms an ionic bond is called a salt. So it doesn't have to be table salt. It could be table salt substitutes such as potassium chloride, KCl, if you will. The compounds are actually ionic, that is, have their ions packed real tight to form this crystalline structure. So it's a crystal lattice structure. And we see the ones that's positive, that would be the sodium in this case, and then the negative would be the chlorine. And the lattice structure in itself we see quite often in everyday life, like a lattice fence, and the strong attraction of positive to negative results in its formation, if you will. And these are very strong bonds. And there is a picture, if you will, of a lattice fence. So if you see a lattice fence, you've gotten the general idea of a lattice or crystal lattice structure. Also, if you notice, there's gaps in the lattice fence, just like there's gaps in the lattice structure. And that's interesting because of the fact that there's applications nowadays to make use of that. As a result, ionic compounds have a very high bond strength. And you hear this quite often with ionic bonds, that they do have very high bond strength. They're very durable, very strong, and when they're very durable and strong, that gives us a clue as to ionization energy in terms of it's going to be a lot of it or a little bit of it. When determining the strength of an ionic bond, scientists look at three things: hardness, melting point, and boiling point. And melting point, as a side note, you do see this often in the winter when we have salt put down on the roads to break up the ice. The salt is actually helping to lower the freezing temperature of the water. Water typically freezes around 32 degrees Fahrenheit. And when it does that, it makes it, of course, slippery for us to ride vehicles or even ride horses. But if you lower the temperature maybe down to 20, 15, even closer to 0, and it's 32 degrees outside and stays that way, then we're fine. And that can actually keep the water in a state that's liquid and it will not freeze, which will make it easier for travel. So the hard, rigid, brittle crystalline structure, as we see, ionic compounds. If you know nothing else about ionic compounds or learn anything else from this, just understand that hard, rigid, strong bonds are associated with ionic compounds, crystalline structures. So anything that appears to be a crystal, chances are it has a ionic bond or bonds on the inside of it. And so when you actually look at the structure and break it away, it will break away in a characteristic fashion, if you will. And you can see with the hammer being applied, it's going to knock it and it's going to slide away. Let me do it. Yeah, there we go. And break away. And that's pretty much how crystalline structures do. When they break, they slide away and break away, and you have the repeated structure all over again. Here are examples of salt compounds and how they appear. And typically they do look like ice cubes, look like regular chunks and ice cubes. Even sea salt has the same appearances, even when you look at it from a not necessarily a distance, I'll say, but when you look at it all together, jumbled in a bowl, a bag, or a jar, has the same type of structure. But this in itself is a zoomed in electron microscope images to show us how they really appear. And of course, the spaces in between the bonds are definitely microscopic, so we can't really see those. But as far as melting point and boiling points, the intermolecular forces, which means the forces that hold the molecules together, the forces that hold the molecules together of that very compound. Remember, elements are, no, reverse it. Atoms are to elements as compounds. All right, let me try it again. I mixed it up. All right. Atoms are to elements as molecules are to compounds. And we talked about that last Friday. So with that being said, molecules make up the compound. And you have to have the compound held together. And we look at the forces that do that. They're very strong and they require more energy to break. So therefore, high temperatures are a result of more energy being required to break those bonds. Therefore, ionic compounds would have what type of melting and boiling points? High. H-I-G-H. High melting and high boiling points. It would take a large amount of energy to break them up. All right, when ionic compounds are solids, they are non-conductors of electricity, meaning that they are insulators if they're not conducting electricity. So therefore, they're not a good thing to use. But it's very interesting how this works out. The reason is that they're too tightly packed. There's not enough space for electrons moving around inside the compound. So it's not going to happen. So here we have the compound of salt, if you will. Electricity comes to it. Nothing happens. However, when they're in water or they begin to melt, they begin to separate, which means they begin to break up. That means, for example, salt. And when it begins to break up, it breaks up the ions of the sodium and the chlorine, and they're floating around, moving around inside the water. And that's called dissociation. So they dissociate. And then they can carry and move electron charge, for example. So here we are. It goes in. Boom. They break away. You put electricity to it. Electricity will carry the charge. And now you have zap, zap. You have it electrified. Now keep in mind, electricity is nothing more than electrons flowing, or the flow, F-L-O-W, of electrons. That is what electricity is. Electricity cannot flow or occur unless you have the means for whatever's carrying it to make that connection, to have it where one electron go from one ion or within inside ion to another. So that gives us a hint as to how metallic lattices or metals operate, if you will. We'll get into that later on, I believe within the next week. So special name for ionic solutions, one was called electrolytes. We actually see electrolyte all the time, and we might even drink it. So those of you that play sports, if you will, and that would be Gatorade or things such as Powerade, even Smart Water. It has electrolytes in it. Electrolytes are typically salts dissolved in water. And what they do, they help boost your ability on the inside of the human body to actually carry electrochemical signals as you need to in the human body, especially for your nervous system. And these are nothing more than salts or ionic compounds dissolved in a medium. The medium could be anything. It could be water, or it could be what's called an aqueous solution. Aqueous refers to water. Aquatics, Aquarius, aqueduct. The AQUA refers to the existence of water, like Aquaman, for example, who was basically a foreshadowing of Neptune. But anyway, you get the idea. And so electrolytes broken up in water or excuse me, salts broken up in water are electrolytes. The most common medium is water, H2O. When you hear electrolytes, think electricity. So does that mean Gatorade can carry a charge? Yes, it can. Conductivity in action. So if we look at an example here, we can see water, and we can see what's called electrolysis. Electrolytes are usually produced by a process called electrolysis. And electrolysis is when you put two electrodes like we have in front of us. In this case, we have a light bulb at the end of those two electrodes. And what's going to happen is that the electricity is flowing between those two electrodes from the cord that's in the back of it, which is this black cord here. And what's going on is that the black cord is right here. You have water, but this water needs in it to carry a charge. So if we took sugar, for example, sugar's covalent bond. Covalent bonds, we know, share electrons between the two or more elements mixed into that compound. So we need something that's going to actually break up in the water and carry a charge so that the electricity, the flow of electrons, can flow. So in that case, we can't use a covalent bond, we have to use ionic bonds or bonding, which would simply be table salt or salt itself. And so therefore, the flow of electrons can happen and go from there. You might recall last week when I said water is a bad conductor, but the things in it could carry a charge or can carry a charge, but they have to be things that can carry a charge, and ionic bonds or the products of ionic bonding, or things that's bonded with ions or ionic bonds, if you will, can do that. So if it was potassium chloride, it can do it. If you took the salt that's just put down in the winter, which is a different type of salt, and I think it's I have to think about what it is. I think it's NaCl or something like that. That salt in itself, and I may be wrong on the chemical name, but if we put something down like that in here, it's still a salt, it can carry the charge. Ionic bonds are exothermic. What that means is this: they release energy. And energy usually is in the form of heat. So the word exo, or as an exothermic, means to exit or to release or to go or to flee, move. So words like exit, that mean, this is the way out, if you will. Or the word exodus from the Old Testament of the Bible means to move or to go, if you will. Exoskeleton, outer skeleton, outer shell. So thermic, which means or refers to thermo or to heat, fire. So exothermic means the release or the going or the flowing of heat. Endo is the opposite, means to enter or within. And it takes energy to break bonds after they are made. So chemical reactions are going to involve bonds being formed, bonds being broken, or both. As I mentioned before, and this is where we start to get into that right here, is that the bonds are starting to be formed or broken, if you will. In this case, they're being broken. Energy is called the lattice energy. It is the energy that is required to form this structure. More about lattices: the size of the ions,